And welcome back, everybody. So in this lecture, I will talk about biodegradation and especially, monokinetics and how this monokinetic works. So one thing that's important to notice is that when you have organic pollution, especially, let's say this fuel spill, right, you can count on bacteria essentially to clean it up, right? And we already did example in our second course towards the end of our wells hydraulics course. Excuse me. So during the end, towards the end of the wells hydraulics course, remember we had examples of pump and treat, right, and how those well system of injection wells and pumping wells and then surface treatment work. So a lot of times, when we did that 4-well isolation cell, if you remember from that course, what we're trying to do is, facilitate or encourage biological growth inside the aquifer so that it takes care basically of the pollution for you. Here are shale, shale gases, right? The extraction of gas in the US. So all these deposits where there's a lot of groundwater pollution due to the extraction of gas, from gas fields. So again, elevated levels of diesel range organic compounds in groundwater, right, due to shale gas operations. Here's an example of how those work, and again, you can see the fracking here, right, and then you're trying to extract those bubbles of gas, but if you have leakage into your aquifers, then you find elevated organic compound in the groundwater that people rely on oftentimes to drink. So again, one way you can take care of those organics is by essentially, organics are rich carbon compound, right? So reduced carbon compound. So of course you can just use heterotrophic organisms, so bacteria essentially, to chew on it and literally clean it up. There's some hope here because very recently, so this is April 2020, so fairly recently, there was a Supreme Court ruling here in the United States that basically says that scientists should be listened to when we rule on groundwater health or groundwater quality. So that was quite interesting. Okay, let's get back to the topic here. So how is that monokinetic working, or how does biological growth essentially work, right? So here I'm just comparing an exponential growth to what we call a logistic growth, or again, the monokinetic essentially. And I'm using this model because it's maybe a little intuitive. So if you think of it as a change in number of organisms versus time, and here you have a reproduction rate and the number of organisms you start with, right? So if it's an exponential growth, right, this R is just, a constant number, so it's an exponential. And this is very similar to the first order kinetic we've done before, right? We can solve this very simply, separate the variables, solve, and you can see that's just an exponential growth. So meaning that population is going to grow exponentially. When you have a logistic growth, right, now the rate at which the population grows depends on the size of the population, meaning there's a maximum population that the environment can support essentially. So that's what we call K here. And, as the number of individuals in the population approaches K, right, the rate of reproduction or the rate of growth decreases, right? So again, because there's a maximum, so think of it as when N is K, right, when there's as many individuals as the environment will allow, right? So if N is K, K minus K is 0, and then you stop growing, right? You cannot grow anymore. So there's a saturation, if you will. That's like a saturation kinetics, where there's a maximum growth rate, and then there's a maximum number of individuals that you can attain. So again, remember that there is basically, if you look at this equation, it's the same except for this tweaking here that just, it's like a knob basically that says, hey, if there's too many people, we can't grow as much or as fast, right? So we're saturating and we're reaching that, again, steady state or equilibrium population number. And this is typical, again, of what we call monokinetic or logistic growth for population as opposed to exponential growth here. So what does that mean for chemistry, right? For reactions instead of populations? Well, it's the same, right? So dCdt equals mu c, that would be a first order rate, or mu max, right? So if mu now, instead of being constant, depends on the substrate amount, right? The amount of substrate available, now you can see how this is exactly similar to a logistic growth, right? So now instead of growing, instead of the reaction being a first order reaction and decreasing, exponentially, now it's decreasing to a plateau. Basically, there's some equilibrium that is reached in the population. Now let's model, let's look at equations or a model of microbial growth and organic contamination, right? So if you have H, O, and M, where H is a hydrocarbon, so again like an organic compound, O is some oxygen concentration. Remember that we're using oxygen to respire the organic carbon, right? So it's just like us when we eat a steak, right? We're using oxygen to burn basically the carbon and release CO2, right? So it's like this is the sugar plus oxygen goes to, right? That's what we respire, that's what we eat, sugar, and this is the oxygen that we use to burn the carbon. So same thing. Now here, total aerobic microbial concentration. So we're modeling the microbial growth, right, along with the carbon and oxygen dynamics together, okay? And you can see here that all of our rates depend on oxygen and hydrocarbon concentration and monokinetic rates, and now our microbial population also depends on how fast they can process the carbon and the microbes. And of course, when you look at the microbial population, you also have some birth and death processes. So B is decay rate, so that's basically a death, right? A death process, so they're dying. And then Kc here is decay rate of natural organic carbon. So there's also an added process that doesn't depend essentially on the microbes themselves. Okay, now the point here that I'm trying to communicate is that at this point in our lectures, right, we are able to model, to understand what that monokinetic means, and we can model the evolution of oxygen and carbon and microbes, let's say in a polluted aquifer, over time based on monokinetics if we know all those constants, right? Now, if we put this together with transport, and that's really where I'm getting to here, so now we have a model of population growth and pretty advanced kinetic modeling with a monokinetic. Now we can put this together with, look at this, transport, right? So we have advection dispersion, and remember what we're doing right now in this fourth topic here is looking at reactive transport, so adding things onto the transport equation. So now the things we're adding are getting complicated a little bit, but they're still, at the essence of it, dCdt equals dispersion, advective flux, and now some reactions that can follow, let's say, the monokinetic, right, or the first order kinetic. Okay, so now we have a complicated system, but we can understand, we can piece it out, and all those equations being coupled, if you will, by here the oxygen and the hydrocarbon, the oxygen and the hydrocarbon, and then finally the microbial, right, also move. There is a retardation factor right here, 1/r, right? This is a retardation, and then these whole monokinetic and birth and death processes. So now we can really start, looking at advanced problems. Okay, I leave it there. In the next short video, I will go through an example that uses essentially a paper that uses all these concepts and show you how we can now, look at literature and read, current research essentially based on all those principles. Thank you.